Hello everyone, my name is Saul Herrera. I'm from Mexico and I am a master's student at the University of Guadalajara, where I focus on sustainable technologies for food production. Today, I would like to share a project that combines environmental sustainability, renewable energy, and food security, all through a product made for what many people consider waste: fish residues. Let's begin with the challenges we face in rural areas of Mexico. According to the Mexican Ministry of Health, around 12% of the population, that is more than 15 million people, suffer from some form of nutritional deficiency. In rural and coastal regions, this is often due to poverty, isolation, and limited access to nutritious food. Ironically, many of these communities are located near natural food sources like the ocean or freshwater reservoirs, but without proper infrastructure or technology, they often waste resources that could help improve their diets and income. One clear example is the tons of fish waste generated every day in fish markets, small processing plants, and fishing villages. This waste is typically discarded, creating environmental problems such as bad odors, water contamination, and pests. Fish residues can be used to produce fish meal, which is a nutritious product rich in healthy fats, proteins, and important minerals like calcium and phosphorus. However, producing fish meal the traditional way is very energy intensive. You need to cook and dry the waste quickly to avoid bacteria growth and to preserve the nutrients. This makes it expensive and difficult, especially for smaller rural communities with limited access to energy. Fish meal is commonly used in the agriculture and livestock industries and can also be incorporated into organic fertilizers, animal feed, and even nutraceuticals. Our idea is to adapt solar energy technologies to cook and dry fish waste using low-cost equipment. This way, rural communities could process their own waste and produce safe and useful products, while also protecting the environment. To test this, we designed a small-scale production process and carried out all experiments in Colotlan, Jalisco, a town located at 1,720 meters above sea level, close to the 23rd parallel, which offers good solar radiation most of the year. We start by receiving frozen tilapia waste, which we cooked for 4 hours using a Hines 2.0 solar panel cooker. This system uses reflective surfaces to focus sunlight onto a cooking pot, reaching temperatures of up to 100 degrees. After cooking, we press the material to remove excess liquid and form what is called a pressed cake. This pressed cake was then tested in the lab to make sure it was free of dangerous bacteria like Salmonella and to measure the levels of Mesophilic bacteria and coliforms using the official Mexican food standards. Then we move on the drying stage. We use a natural convection solar dryer. We spread the pressed cake in 1 centimeter thick layer and monitored the drying process. During all stages, we took measurements of moisture content and water activity before and after cooking and drying. At the end, we ground the dried material to produce fish meal and add BHT, a common antioxidant to protect the fat from going bad. We also measure the nutritional composition of the final fish meal, focusing on proteins, fats, and ash content. Throughout the process, we keep track of the internal temperature of food solar devices every 15 minutes, and we also record the weather condition using a weather station. Using this data, we created a drying kinetics curve based on how much weight the product lost over time. Here are some of the most important results for our study. First, we use a drying bed of 1 centimeter thickness and complete the drying process in one solar day. Then, the yield was 17.6% based on the original weight of the fish. Even in autumn, the solar cooker reached 80 degrees and the dryer reached 60 degrees, which are good temperatures for safe and effective processing. About the drying rate, this increased with the level of sunlight, and the drying curve show a pattern similar to other food products. And the UV radiation help reduce microbial load. However, prolonged exposure may affect some nutritional properties due to its short wavelength nature. About the microbiological analysis, lab tests showed no salmonella, no coliforms, and no mesophilic bacteria in the cooked and the final dry fish meal. In this slide, we can see the culture plates where they show no bacterial growth in treated samples, while positive and negative controls behave as expected. And about nutritional analysis, these reveal a high protein and ash content with a moderate fat content, which is particularly important for promoting food sovereignty in rural communities. At the end, we conclude that the application of a double thermal treatment to fish waste through cooking and solar drying result in the production of safe and harmless fish meal. On the other hand, the final values of moisture content and water activity ensure the stability of the fish meal against microbial and enzymatic deterioration. And this proposal highlights the potential of renewable energies in the agri-food industry, particularly in rural Mexican communities with limited access to the conventional energy sources. And well, that was all. Thank you so much for your attention.